Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We have the subject called compiler design, and we are studying the LR parsers in this episode and even in the previous episode also. So, LR parsers are the most efficient parsers coming under the bottom of parsing categories, and it is most powerful also because of almost all the programming language constructs could be expressed in context free grammars, and it is possible to construct parsing table, that is LR parsing table for that is all the programming language constructs, or the grammar meant for all the programming language constructs. So, that is the reason why the LR parsers are becoming more efficient. And also we have seen that there are three number of methods for constructing the LR parsing tables. So, one is the simple LR parser, that is SLR, and the second one is canonical LR, that is CLR, and the third one we had that is listed is the LALR, that is canonical look ahead LR parser, and all of them will construct the same LSLR, the same LR parsing table, but the methods being used for constructing the parsing tables so will be different. So, SLR is following a strategy and canonical LR is following another strategy. So, the LALR is even following a different strategy for coming up with the parsing table. But whether the method is going to be SLR or canonical LR or LALR, the table being obtained is going to have the same structure. And also we have seen the configuration of the LR parser. So, which is actually there are two components available. One is the stack component and another one is the buffer component. The buffer is the one where the input is going to be loaded, and whereas the stack is the one where we are having the that is the configuration which is changing. That is how we will be generating these essential forms which are needed for the parsing the string. Also we know that SLR parser, or whether it is going to be SLR, canonical LR or LALR, they will be making use of the right essential forms. So, every configuration, if you just combine them, that is the configuration means the stack component and the buffer component, if you just combine, so we will be having the essential form as output, which is nothing but the essential form obtained using the rightmost derivation. So, that is about the that is the configuration. So, here we have the configuration. So, the S0, X1, S1, X2 and S2, and finally it is going to be XM and SM. What we understand from here is every state, that is a grammar symbol, is bounded by the state, sorry, there is grammar, sorry, every grammar symbol is bounded by a pair of states. And here we have the list of that is these input symbols terminated by the end marker called $. So, if you combine the stack as well as the buffer, that is after excluding the states, we will be having the right essential form. So, now look at that is how the LR parser is going to behave. So, the behavior in the sense like already I stated that there is an initial configuration and there will be a final configuration for each parsing process, and if you are able to move from the initial configuration to the final configuration, then there will be different that is configuration being produced in intermediate stages. So, the number of configurations being produced, or how do we move from one configuration to another configuration, it is all depending upon the that is the grammar and the input symbol. But a change in configuration from the ith configuration to I plus 1th configuration is obtained as a result of either a shift operation or an accept operation or a reduce operation or as an erroneous operation. So, that is what being happening as far as the change in LR, that is parser configurations are concerned. And here we are going to address how the parsing configuration that is the configuration of the LR parser will change for a shift action, and how does it change for a that is a reduce action, and how does it change for a that is accept action, and how it is being handled when we are handling the errors. So, that is what the behavior of your LR parser. So, this process is otherwise called as the parsing process. So, we start with the initial configuration where the stack has only the start state of the automata or this parsing table, and the buffer has the entire string which is to be processed. So, if it is going to be the starting configuration, and then from that we will be changing the configuration continuously to go for the final configuration. As a result of that, we will be having a parsed as output. So, let us see that is how the actions are going to be handled to go for a different configuration from the current configuration. The assumptions here. So, the AI is the current input symbol, and SM is the current state on top of the stack, and now we are going to consult the action in the parsing table. So, that is the action component. We have AI, that is going to be the current input symbol, and SM. So, SM is going to be the row index and AI is going to be the column index, that should be swapped. And now suppose if you are the action entry in SM comma AI is shift S, which means that we go for the shifting the current input symbol from the buffer to the stack, and what is going to be the change in the corresponding configuration. So, let us see the configuration here. The configuration starts with S0, X1, X2, etc. up to XM, with the SM up to that we are having on the that is stack. That is before shifting we are having SM on the stack, but after shifting, so what happens is, so we can go for that. So, we have that is we are having up to this SM, and whereas in the case of that is after the shift operation, we will be going for moving this AI which was actually in the buffer. So, now it has been moved on to the stack, but it is not just a shift operation. So, once we have made a shift operation, so we will be having a grammar symbol exposed on the top of the stack. But as per the configuration of the LR parser, we must always have a grammar symbol bounded by a pair of states. So, on the left of this or just below this current input symbol, that is the symbol which has been shifted onto the stack, we have a state, but over that it is completely empty. So, that is the reason why we check what is going to be the action here. The action here is shift S, and this S is nothing but the state where from we have to resume the parsing process. So, this is the S being shifted onto the stack. So, we will be having the current operation action of SM comma AI, if it is equal to shift S, then shift the current input symbol from the input to the stack, that is as a result of that we are having AI, and after that we will be pushing this number which is nothing but a state number available in the that is your parsing process, which is on the top of the stack. So, now we can say that the grammar symbol AI is bounded by a pair of states, one is called SM and another one is called S. But what is the change made on the buffer? The change which is made on the buffer is one symbol is missing. That is, we had earlier the current input symbol as AI. So, now it is not AI, it is going to be AI plus 1, AI plus 2, etc. up to AN, and finally it is going to be the dollar. So, leaving the new configuration with the top of the stack is going to be S, and the current input symbol is going to be AI plus that is 1. So, this is what being happening as far as the shift action is concerned. So, we just take what is going to be the current input symbol and push it onto the top of the stack if it is going to be shift action, and the shift entry in a parsing table, that is LR parsing table, is always associated or accompanied by a number which is nothing but the state number. So, that state number is also to be moved onto the top of the stack, so that your grammar symbol which has been most recently pushed onto the stack is bounded by a pair of states. And when you are looking at the next action, which is going to be reduce action, so here is the action entry. We have action of SM comma AI is now telling that reduce A deriving beta. So, this reduce A deriving beta means it is going to be the reducing production. So, this reduce A derives beta means you just find out beta on top of the stack as a handle, and this beta is going to be replaced by the left hand side of that beta. By this production, the left hand side of this beta is A. So, find out beta, replace it by A, so that there is a reduction happening, and this reduction is nothing but, in the case of your parse tree construction, collecting few number of child nodes and connecting them with the parent node to form a new subtree. So, continue this process as long as we get that is until we get the root of the parse tree that is labeled with the start symbol of the grammar. So, now we know that is what is going to be the reducing production to be used for the current reduce operation. It is going to be A derives beta. So, as far as the configuration of the parser is concerned, if you want to find out the exact handle that is beta, already we have seen that the grammar symbols are always bounded by a pair of states. So, if you want to completely extract beta out of the stack, it is not just enough to extract or pop up exactly the same number of symbols in beta, but we should go for double the number of symbols available in beta, as every symbol in beta is bounded by a state number. So, that you can see here, that is in the case of x1 we have, there is x1 followed by s1, that is these two symbols are there. Then when you are talking about x2, we are having x2 as well as s2, and when you talk about sm, there is a, and we are having there is a xm minus r, we will be having sm minus r. So, if you want to go for there is popping out this beta completely, so we should go for removing 2 into r number of symbols, where r is nothing but the number of symbols available in beta. There is a parser pops 2 into r number of symbols from the stack. So, when you pop 2 into r number of symbols from the stack, we will find that the xm, sm which was earlier there on the stack is changed to xm minus r and sm minus r. So, initially we had xm minus r and xm and sm, but after popping 2 into r number of symbols out of the stack, so we have xm minus r and sm minus r. So, that popping has been done. So, next what is to be done is going to be a push operation. So, what should be pushed onto the stack is going to be this a. So, where from we got this a is, which is the one from the left hand side of the production called A derives beta. So, after finding beta, find out the number of symbols available in beta, remove 2 into the number of symbols available in beta from the stack and push a onto the stack. So, now once again we have a situation like we are having top of the stack loaded with a grammar symbol rather than a state. So, now the question is, how will you introduce a state on that? So, to introduce the state on the top of the stack, we will go for consulting the sm minus r and a. The sm minus r is a state which is just below the top of the stack, and this capital A is on the top of the stack, which is the most recently pushed symbol onto the stack. So, when you go for go to, already we know that go to is going to be the table entry, that is LR parsing table entry, which is indexed by row wise state number and column wise variables. And here we are having a state number and followed by a variable. So, your sm minus r is the row index and a is the column index, and there is an integer available on that entry. So, if it is going to be a valid move, and there will be an entry which is nothing but an integer, so we call that integer as the state number. So, we get small s, that is state number, as a result of go to sm minus r comma a. So, now what do we do here is find out that state number, push it over the left hand side of the production. Already we have loaded the left hand side of the production with capital A. Now, we are pushing s onto the stack. So, here is the condition being satisfied. That is, your top stack symbol which was earlier capital A is now bounded by a pair of states. One is sm minus r and another one going to be there is s. So, we will be able to see that the configuration has been changed to a new one after processing the reduce action. So, it is going to be that is the identifying the production, which is nothing but the A derives beta, just count the number of symbols available on beta and pop out 2 into R number of symbols and then push the left hand side and push the state number which has been obtained as a result of go to of Sm minus R comma A. So, that is about the reduce action. So, two important actions are that is shift action and the reduce action, and after a short break we shall see that is how it is going to be an accept action and an erroneous actions have been that is considered. We shall go for a short break. Welcome back. We have seen how the shift action and reduce actions are handled by the LR parser. For the shift action, we will be shifting the current symbol from the buffer to the stack and loading the new state number which has been obtained from the parsing table onto the stack. For a reduce action, so we have that is A derives beta, means the number of symbols available in beta multiplied by 2 number of symbols will be popped out of the stack, and we will be pushing the left hand side A onto the that is stack. Then we will be consulting what is there in go to of the Sm minus R comma A, and we will be storing that number which is nothing but the state number that is onto the stack. This is how the action has been carried out. But whereas when you go for the accept action, so we will be just looking at the entry called Sm comma AI as usual, and the speciality about the LR parsing table is the accept action is also incorporated into the parsing table, but that is not true in the case of a predictive parsing table or even the operator presence relation table. So, they will not directly tell you that what is the state where we are going to accept, but as far as SLR parser is concerned or even the LR parsing tables are concerned, the accept action is also incorporated or introduced into the that is parsing table. So, now as usual you find out what is on top of the stack and what is going to be on the current input symbol position. Maybe if you find that the completely all the symbols have been processed, so we will be left with only that dollar. So, we go for what is going to be on the current top of the stack and the dollar symbol. So, if the action is going to be accept, then immediately you can accept the entire string, that is parsing process, saying that the string is going to be a valid one. But if anything is wrong, it will go for an error. That means, when you are looking for action of Sm comma AI, that is if the action of Sm comma AI is undefined. Is undefined means there is no entry has been added, and suppose if it is going to be an error handling parser, then so it is possible to go for that is having the that is erroneous actions. It can be like the panic mode of operation or even the error handling productions. So, some kind of recovery strategy will be included or incorporated into the parsing table, so that if you go for looking at those entries, the appropriate actions as mentioned in the parsing table will be carried out. So, it is fully depending upon what kind of strategy being followed for handling the errors. So, totally 4 possible actions, and the all of them will move from one configuration to the other configuration. If it is going to be the accept, then that is going to final configuration. If it is going to be an error, so that can be either treated as the final configuration, that is an invalid configuration, or it could be considered as an error handling operation, so that the normal execution of the normal parsing process will resume after doing some kind of error recovery strategies. When you look at the next one, that is how we are constructing the parsing tables. So far we are studying how the parsing is done, but the parsing is actually having the that is parsing table plus a driver routine. The job of the driver routine is consulting the top of the stack and the current input symbol position and deciding what should be done from the parsing table and doing everything. But the question is now, how will you construct the parsing table? That is, in the beginning itself we have seen that there is a table generator software or program which will be accepting the grammar, producing parsing table as answer. But how the parsing table is going to be constructed? So, we have to see that the parsing table of an LR parser as a deterministic finite automata. So, it is going to be an automata with states and transitions. The states are as usual, they are numbered with that is integer quantities, but what do we have in each state and how do we differentiate a state from one to the other one. So, it is all because of the parsing process, that is the progress on the parsing process. So, how far we have generated so far, how far you have recognized and what is yet to be recognized. So, two components, that is we are having a production and that is going to be part of some sequential form, and out of that if you find the whole thing as a handle, we will go for a reduce action, but that may not be always possible. We may be even in the beginning or at the end or in the middle. So, how do you know that is what is the state of the parsing? So, we will mark the state of the parsing by introducing the presence of a dot, and the dot will tell you that is how much in a production has been processed so far. So, if you introduce a dot into the production, we call that items as LR of 0 items. So, we will be going for the LR of 0 items, and that is actually used by the LR parser. So, we shall decide on whether to continue with the shift action or with reduce action. So, if you want to still find out the complete handle for reduction, we will go for a shift, or if you find that already everything is on the stack, then you can go for a reduce action. So, these items are available in various states, that is your LR of 0 items are available in the various states of the transition diagram, or it can be considered as the parsing table. So, now this LR of 0 item of a grammar is a production with a dot at some position on the body of the production. See, for example, suppose if you are having A derives XYZ as a production, there are 4 possible items. One is going to be A derives dot XYZ with a dot on the extreme left, saying that so far nothing has been recognized, but still we have to recognize XYZ, and the second one says that X has been already recognized and still we need to recognize Y and that is Z. The third one says XY is recognized so far, Z is yet to be recognized, and this last one says XY Z has been completely recognized, we have nothing else for recognition. So, the first 3 items are telling that it is not possible to go for reduce action because we haven't completed the complete handle identification, whereas the last item says that we have completely processed everything. So, this can trigger for a reduce action. So, what gets reduced is XYZ is getting reduced to that is A, so that we can claim that a reduce action is possible. So, this is what your LR of 0 items. So, now this LR of 0 items are going to be used by the SLR parser. So, that makes a difference whether we are going for constructing the LR parsing table with the help of SLR method or canonical LR method or LALR method. The parser, that is as far as SLR is concerned, it is using LR of 0 items for constructing the parsing table, whereas in the case of canonical LR, it uses LR of 1 items. In the case of LALR parsing, it is using LALR items, that is the merging of your LR of 1 items to produce the that is parsing table for LALR parsing. In the case of our shifted is parsing, so it is actually a deterministic finite automaton that recognizes all the viable prefixes, and every state available in the DFA has a set of items called LR of 0 items or simply items, and hence it is required to construct the canonical LR of 0 items for the augmented grammar G dash. So, we should know that is what is the meaning of a grammar and what is the meaning of an augment, or how the augmented grammar differs from the grammar. The grammar is having the set of all productions as such, it is given from the that is language specification, but whereas the augmented grammar is obtained by introducing an additional production. Normally S dash derives S, where S dash is the newly introduced start symbol and S is the given start symbol. The reason why we are introducing this production into the augmented grammar is, already I said that the LR parser parsing table is having the reduce action incorporated into it. So, to have the the accept action into the parsing table, we must have the augmented grammar. So, if you do not have the augmented grammar, or if you are constructing LR of 0 items for the non-augmented grammar, then the accept action cannot be incorporated into the parsing table. But as a result of converting the given grammar into the augmented grammar, we can ensure that the accept action is incorporated or introduced into the parsing table, so that the parsing will be very much easy. So, that is the reason why we are having the augmented grammar. So, now to find out the LR of 0 items, so we will be having two functions called, one is called the that is closure, and another one is called the goto. So, these two functions will be used for that is constructing the LR of 0 items. As far as the procedure items is concerned, we need to construct the set of all items for all the states available in the grammar, and the collection, that is your C, that is we called as canonical items, collection of items. The first state is actually obtained by the closure of S dash derives dot S, which is an additional production introduced into the augmented grammar. So, once this has been obtained, we know that there is a state already generated on your C, and now it is going to be a repeat, that is process with a symbol, that is algorithm, that is for each set of items I in C and each grammar symbol X, such that goto of I comma X is non-empty, and not in C, we must go for adding goto of I comma X onto the C. That means, when you find out the closure, we will be having one state on our hand, that is in the canonical collection, but we must continuously generate all possible states from the given grammar. So, for that we will be applying the transitions. Since it is going to be deterministic finite automaton, the closure itself is a state, and from that state we will continuously generate the other states, so that we will be able to that is complete the entire transition step, that is a deterministic finite automata formation. So, to find out the continuous or consecutive states, what we do is applying the goto function. So, initially we will be having one state, and then we will be going for the next state by applying the goto function for the grammar symbol, which could be either the that is lowercase letter, or it can even be uppercase letter. That means, it can be even a terminal or a variable. So, you continuously do this, and at some stage we will be having a situation that from all the states, for all these the grammar symbols, the transitions have been evaluated. So, that is going to be the end of your canonical collection. So, the process will be repeated. So, we will be going for that is continuously generating the various states, and when we find that a state where no more new state can be identified, we can stop the process, saying that the canonical items have been completely evaluated. So, there are two more procedures, one is called the closure and another one is the goto. So, those must be learned in order to produce the that is the entire LR of 0 items. So, to summarize, so we have studied the behavior of the LR parser while parsing the given string, and then we have studied the LR of 0 items and the role of the LR of 0 items. The LR of 0 items are actually used for constructing the SLR parsing table, that is going to be simplest one among all the three parsing table construction methods. And to the question component, so what is going to be the configuration of the LR parser and how LR parsing is done with different actions like shift action, reduce action, accept action or erroneous actions, and how the LR of 0 items for the given grammar are constructed, and what is the meaning of the or significance of this LR of 0 items. So, the 0 stands here means that the parsing actions are not based on lookaheads. So, in general we will be having LR of k items, where that k stands for, that is how many number of symbols are considered in advance to decide on the parsing action. The parsing action can be either shift action or reduce action. So, to find out what is going to be the appropriate action, how many lookaheads we consider. So, if we consider 2 number of lookaheads, then it will be called an LR of 2 grammar. If you decide based on one lookahead number, one lookup symbol, then it will be considered as LR of one grammar. So, that is about the possible questions from this that is component which you have seen as far as this part of episode is concerned. So, with this I complete this episode. Thank you all.